أمي المبعوث رحمة للعالمين.
So with that high-level overview of the course, I propose that we begin to take a look at what computer science itself is and what it is we're going to be doing over the next several weeks at this lower level than 2. So what is computer science, right? If you're maybe like me or new people like my friends in high school, you probably assume that it means programming. And that's absolutely a big part of it for a lot of people, because with code you can write, you can express ideas and solve actual problems, especially involving data. But computer science itself is really the study of information, if you will. How do you represent it, and how do you actually process it? And in that sense, computational thinking is just the application of ideas from computer science, a course like this, to problems of interest to you. Again, in the arts, humanities, sciences, social sciences, whatever the domain of interest is to you. So with that, if computer science is all about information and with it the solving of problems, well, what does it actually mean to solve a problem? Let's see if we can't propose a model into which all of the lessons learned will ultimately follow. And I propose that this is problem solving. You've got some input, which is like the problem you want to solve. The goal is to solve it, so that's the so-called output. And then somewhere in here, the proverbial black box, is some kind of secret sauce that gets the work done. And in the coming months, we'll have to decide, well, how are we going to represent these inputs and outputs? And really, how do we code up? How do we write solutions for what it is that's solving the problem of interest to us? So when it comes to representation of information, like, there's a lot of ways we can do this. And for instance, if the problem at hand quite simply is to take attendance at the beginning of class on the first day of school, well, how could we go about doing this? Well, we could actually use a system called unary. Well, what is that? Well, that's a fancy way of saying 1, 2, 3, 4, 5, maybe 6, 7, 8, 9, 10. And I can use my digits, pun intended, on my fingers to actually count everyone up. And eventually you need toes and whatnot if you have to count so high. But unary is a very simple system of using a single symbol, a human finger in this case, to just solve some problem, like counting the number of people in the room. Let's make this slightly more technical for a moment, a little more mathy. That's just called base 1, where the base under which you're operating has 1 digit in it, like literally a human finger, and maybe multiple such fingers if you need to count higher. But of course, most of you, if not all of you, generally vaguely know that computers use something other than unary. And even you and I probably don't use this that often. They use what language or alphabet instead? Yeah, so binary. So binary is indeed the system that computers somehow use. So in this case, bi implying 2. And so computers have 2 digits, it turns out, at their disposal. And in fact, if you've ever heard the technical term bit, which is like a smaller version of a byte, more on that soon, well, a binary digit is the origin of that term bit, because if you get rid of some of the letters and are left from binary digit with just bit, thus is a bit. A bit is just a 0 and 1. It's 2 more digits than you might have on your own finger. And of course, it's fewer, though, than you and I have. You and I typically use, as humans, the decimal system. Dec meaning 10, because you and I generally use 0 through 9. So on the one hand, another pun intended, you've got unary. Computers use binary. We humans generally think and talk in terms of decimal. But at the end of the day, these are fundamentally going to be the same thing, which is to say that it's all pretty accessible to us. Even if you're not a computer person, I dare say you're about to be. So what is a bit? Well, a bit then is a 0 or a 1. That is a so-called binary digit. But how do computers only speak in binary? How do they solve problems, represent information using only binary? Well, at the end of the day, if they want to represent 0 and 1, we need to do so physically somehow. And I dare say that maybe the simplest way to think about a bit, a 0 or 1, is like a light bulb. And so by human convention, let's just assume that if you are a computer, be it a laptop, desktop, phone, or the like, and you want to represent the number 0, you know what? You just keep a light switch off. You keep a light bulb off. If by contrast, you're that same computer and you want to represent the number 1, you take that same switch, that same light bulb, and just turn it on. So a light bulb that's on represents a 1, and a light bulb that's off represents a 0. So why is this relevant to computers? Well, at the end of the day, you and I are charging our laptops or phones at night. So there's some like physical resource being replenished there, whether you're on battery or some power cord. And so inside of a computer are just thousands, millions of tiny little switches nowadays. You can think of them metaphorically as light bulbs, but they don't yet actually shine light. But there are tiny, tiny little switches. And those switches, if you've ever heard the term, are just called transistors. So like computers have millions of transistors that can either be flipped on to represent 1s or flipped off to represent 0s. And from that very simple mechanism, electricity is there or it's not, a 1 or a 0, computers can actually count obviously from 0 to 1, but it turns out even higher if they use a little more electricity as well. So how might I do this? Well, let me go ahead and propose that I just grab one of our own light bulbs here on stage. This one's off. So for instance, if this were miniaturized inside of your Mac, PC, or phone, this would be a transistor. And indeed, here's the little switch on the bottom. And if your computer wants to represent a 0, it just leaves the switch off, and the light is not shining. If you want to represent a 1, well, now I've counted as high as 1 because the switch is now on. I've grabbed a little electricity. I'm holding on to it inside of the computer. And so now I see that this is a 1. All right, but unfortunately, with just one switch, one light bulb, I can only count from 0 to 1. How do I count out higher, might you think, intuitively? Say again? Yeah, so more light bulbs. So let me do this. Let me just grab something to put these on so I can use a few of them at a time. And let me propose that here, instead of having just one light bulb, let me give myself maybe 3 in total. So all of them are initially off. And if you think of this in miniature form in your mind's eye, this is like a computer with 3 transistors, 3 switches, representing now the number you and I know as 0. Why? They're just all off. So how does a computer go about representing the number 1? Well, it turns on one of these light bulbs. And how does the computer represent the number 2? Well, you might think, if I may, you just turn on a second light bulb. And if you might think, how does a computer represent 3? You just turn on the third light bulb. And so as such, with 3 bits, a computer would seem to be able to count from 0 on up to 1, 2, 3. But it turns out if I'm a little smarter here, I can actually count higher than that. Why? Well, I'm just considering like the combination of bulbs being on here. What if I do something like this? This is still 0, I will claim. But what if I propose now that this will be how a computer represents 1? On, off, off. This, though, will be how the computer represents 2. Notice I didn't turn on the same 2. I'm just turning on the 1 in the middle. This, I now claim, will be how a computer represents 3. This is going to be, in just a second, how a computer represents the number we know as 4. And yet I'm still only using 3 bulbs. This is going to be the number the computer represents as 5. This is going to be how the computer represents the number 6. And then lastly, it turns out with 3 light bulbs, if you're smart about it, you can count, it seems, as high as 7. Now, even if you kind of lost track of like what I was turning on and why, I claim there were 7 different patterns, from all of them off to all of them on. But notice that I started to permute them. I took into account which ones were on and which ones were off. Why, though, do these represent the numbers we know as 0 through 7? Well, let me go ahead and maybe let's do this. Instead of just considering there to be light bulbs, let's assign some special significance to each of them based on where it is. And maybe for this, could we get maybe 3 volunteers? 3 volunteers? OK. You're being volunteered. OK, come on up if you want to go over to the stage there. Yeah, you want to come on up as well? And over here as well. So there's some stairs on either end. Maybe a round of applause for our first volunteers of term. All right, so you are number 1. And if you want to go ahead and stand roughly right here. How about you want to be number 2? OK, come on over and right to the right of here. And you'll be number 4, it turns out. And if you want to come over here on this end, let's give you all a moment to introduce yourselves briefly to your classmates if you'd like.
Hi, I'm Ellie. I'm a senior.
Nice to meet.
I'm Rayhana, and I'm a first year.
Welcome.
Hi, I'm Joseph, and I am a first year.
Welcome. All right, so glad to have all 3 of you up here. Thank you. Let me propose now that we'd like you 3 to represent, how about the number 0? And I claim now that if each of you now represents a switch, you have sort of fancier light bulbs now. 1 is a 1, 1 is a 2, 1 is a 4. But each of you still just has a switch on the bottom, in fact, of your plastic devices. I claim these 3 volunteers are representing the number 0. Let me ask you all now, how might you represent the number 1? How should you cooperate here? OK, so we would have on, off, off, which I think matches what I did with my 3 light bulbs as well. If you want to go ahead and turn yours off, how might you all 3 represent the number 2? OK, so off, on, off now, from right to left. How would you 3 represent the number 3? So that's why my 2 light bulbs went on at the end. How would you 3 represent the number 4? Perfect. Number 5? Number 6? And number 7? All right, and give us one more. How would you represent 8? OK, you can't. How about then one more volunteer? One more volunteer. OK, come on up. All right. What's your name?
My name is Moeen.
If you want to say it there.
My name is Moeen.
All right. And Moeen, you're going to be number 8. And if now you all, actually, let's make this, how would you represent number 8? All collectively as 4 bits or 4 switches. OK, 8. And now lastly, give me 15. Everyone's awkwardly doing arithmetic in their head. Oh, using unary. 8, yeah, is everyone? 8, yes, OK, round of applause. OK, thank you all. If you want to leave your numbers over here, we have a CS50 stress ball for you. But thank you for volunteering. You can turn those numbers off and leave them over here. So thank you. So how do we go from there to creating these patterns? Well, even though we still had 3 bits initially and 3 switches, later 4 bits and 4 switches ultimately, we still used the same approach fundamentally to actually representing information. And now why were they those patterns, and why did I very deliberately have our volunteers line up in that way? Well, I wanted them using base 2, aka binary. But with binary, there come certain rules. And even if you're not familiar with binary beyond that it exists and relates somehow to computers, it's actually pretty much identical to the system you and I use every day, known as base 10, aka decimal. So let's consider, if you will, by rewinding to primary school for just a moment, like how decimal works. And you'll see that even if you're not a computer person, you actually are. You just have to tweak your mental model ever so slightly. So here is the number that you're probably viewing as 123. But why is that? Well, it's not really 123. These are just this is just a pattern of 3 symbols on the screen. 1, 2, 3. And your mind is sort of rapidly assigning mathematical meaning to them. 123. But why is that? Well, if you're like me, you probably learned back in the day when you have a 3-digit number like this, the rightmost number is in the ones place. The middle digit is the tens place. The leftmost digit is in the hundreds place. And why is that relevant? Well, if you then quickly do some mental math, as you and I just do instantly nowadays, that just means 100 times 1 plus 10 times 2 plus 1 times 3. Of course, 100 plus 20 plus 3 gives us the number you and I know as 123. But beyond that, how do we get to just 2 digits instead of as many as 9 in the decimal system? Well, let's generalize this. In the decimal system, you and I know if we've got 3 digits represented by these hashes here, yes, it's the ones place, tens place, hundreds place. And if we keep going, thousands, 10,000s, and so forth. But why is that? Well, base terminology is now a little more germane. That's technically the 10 to the 0th column, the 10 to the 1, 10 to the 2. So these are powers of 10, where 10 is your base. Computers just simplify things a little bit, because computers at the end of the day only have access to electricity on or off. They don't have access to like 10 different types of electricity, just 2 on or off, if you will. Well, they just use a different base. And the rightmost digit would be in the so-called 2 to the 0s. Then the middle digit is 2 to the 1. The leftmost is 2 to the 2, aka 1's place, 2's place, 4's place. And as we kept going, 8. And if we keep going, 16, 32, 64, 128, and so forth. But the idea is fundamentally the same. So why is this how the computer represents the number you and I know as 0? Well, off, 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 from right to left, or in this case, left to right, is just 0. Why? Because that's 4 times 0 plus 2 times 0 plus 1 times 0 is, of course, 0. This is why 001 represents 1. This is why 010 represents 2, and 3, and 4, and 5, and 6, and 7 on up. And why did we need a 4th bit to represent 8? Well, we kind of needed to carry the 1, so to speak, using our familiar human terminology. But for that, we need a 4th bit, another transistor. And this now represents the number 8. And that's why we ended with on, from left to right, off, off, off. So I keep saying on and off, or the light bulb is on or off. But really, I just mean 1 or 0. And so computers and we humans think of things digitally as just being 0s and 1s. But mechanically, you can think of it indeed as these light bulbs. But here already, I dare say there's a bit of evidence of things that can go wrong. What happens if you're trying to count to 8, but you only have 3 bits? You have a really low-end computer. And so the computer tries to count from 0 to 1 to 2, 3, 4, 5, 6, 7, and tries to count to 8, but you don't have a 4th bit available. You can't just grab someone from the audience. Well, what might a computer do? A computer might count from 0 to 1 to 2 to 3, 4, 5, 6, 7, and then accidentally, I dare say, back to 0. And if you ever heard of the Y2K problem back in the year when things rolled over from 1999 to 2000, very similar in spirit. It turns out bad things are going to happen in 2038 because of the same kind of reason. Computers nowadays tend to use not 3 bits, not 4 bits. They tend to use 32 bits for a lot of information. And unfortunately, with 32 bits, long story short, you can only count as high as 4 billion. And long story short, computers, Macs, PCs, phones, generally keep track of time in terms of the number of seconds from an arbitrary date in the past, January 1st, 1970. And it turns out if you're keeping track of seconds using 32 bits, but you can only count up as high as 4 billion, computers are not going to be able to count us in that current form past the year 2038. Why? Because we're going to carry a 1, and then all of a sudden we're going to think we're back in 1970. January 1st. Now, what might the solution to that be? We'll talk about it. You just throw hardware at the problem. And so thankfully, modern computers now are actually upgrading to 64 bits. But all of this are the kinds of terms and such you'll see in the real world ultimately. Now, a bit's not very useful. Even 3 bits, 4 bits, not that useful. You can count to 7 or 15. Generally speaking, bytes are a more useful unit of measure. And anyone familiar? How many bits is in a byte? Yeah, so 8 bits are in a byte. You can think of it as an octet equivalently. In some contexts, there are nuances there, but think of a byte as just being 8 bits. And that's just a more useful measure. So what does this mean in real terms? Well, if you've ever downloaded like a music file or a photograph or a video, those are measured in bytes, probably not small numbers of bytes, probably kilobytes for thousands of bytes, megabytes for millions of bytes, gigabytes for billions of bytes, especially for video. That just means you have a lot of patterns of 8 bits, some combination of zeros and ones on your computer's hard drive. Here then, with a byte of bits, 8 bits is how a computer would typically represent the number 0. And if that same computer uses all 8 of its bits, its full byte to change it to 1, anyone who's quick with math or have seen this before, how high can a computer count with 8 bits or 1? Yeah, 255. Why is that? Well, we're not going to turn this into a constant math exercise. Indeed, after today, we're not really going to think about or talk about bits at this low level. But this is the ones place, 2s, 4s, 8, 16, 32, 64, 128. And if I do all of that math from left to right, that indeed gives me 255. It ignores how we might represent negative numbers, but perhaps more on those some other day.